So recorded. Okay. So the first question is regarding the transfer-based attack, and then how really we can find adversarial noise by computing the gradients, right? So, okay, in general, so the whole field of robustness is about how to really find this adversarial vector that we add to the image to make it so that it fools the model, right? And now, so in general, we train neural network to minimize the loss. So in that case, basically we have we compute the gradient, and then we basically subtract the gradient from the parameters, right? So here what's happening is that we compute the gradient and propagate the gradient back to the input image. And here what's happening is that we change the image, in this case, to increase the loss, right? So increase the loss for the specific target class, right? Or we can do the opposite. So we can also have the targeted example, where we have another class that we want to predict the model for. So we want that model predicts another class. And actually, we compute the gradient for the input image, and we do standard procedure that we subtract the gradient from the values of the input image to minimize the loss of this image on the specific target class. So we have this either targeted, which are examples, or untargeted ones, which just change to any class, right? So is there any specific slide to this first question?
How we can do this? Yeah.
Okay, how we can do that? Okay, so you mean how we can change the image to fool the model?
Yeah, how actually for defense, we want to find the adversarial noise, and I don't understand how we can do that.
For defense, for the entire training. So is that the same way as for the attack? So basically,
so only train on the adversarial example, and that's it. Yeah.
So yeah, so basically you can train just on visual examples. So ultimately what you are doing is that you are augmenting the input samples by using the adversarial noise. But basically computing the adversarial noise for the adversarial training was the same as computing the adversarial noise for standard attack. It's the same procedure. Okay, so I think that I think that I did have this also at some point. Okay. Okay, maybe it's also worth mentioning. Okay, so I have two cases. So basically, maybe I can start basically from that. So if we have an untargeted case, actually what we are doing is that we are maximizing the loss on the true class. So y sub true is the true class for the given sample. So we want the model to predict any other class. In this case, we take the gradient, we backprop to the input image, and we then add the gradient to the input image to increase the loss of the model on this sample, right? So here in this case, we want the model to predict any other class apart from y sub true. But we can do another approach, which is targeted. So in this case, we choose a specific class. So let's say we classify the dogs versus cats, right? And then model should predict, let's say, y target is, y true is, for example, dog, right? And we want the model to predict cat. And actually, y target would be our cat. Then actually it's the opposite. So we had plus to full model to any other class. We have minus because we do the same as for the training. So we minimize the loss of the model on this target class, in this case being cat. So there are these two different approaches, how we do optimization, depending on how we go, right? Okay. Any questions regarding these two types of the attacks? Okay. And I think there's also other question from Sarah. In adversarial training, we can make the decision boundary more complex to defend against adversarial examples. My question is, how can we find a balance between complexity and robustness? I mean, how can we make sure that our model is robust to adversaries and at the same time does not overfit? Okay, so I think that there are two aspects here. One of them is how to make model robust. Other aspect is how not to overfit, right? So there are a couple of really couple of factors that decide if model overfits or not, right? So maybe let me go to the proper slide. So I think that you referred to this slide, right? So actually what's happening here is that, okay, so simple decision boundary is basically if you have simple case, maybe this is enough, right? Here actually what was the problem is that the samples, so you have this basically blue squares, right? This expresses that the model should still predict this, let's say, class blue, but the model has not enough learning capacity to express this complex decision boundary. And then you can actually find this some examples that still, I would say, maybe look exactly like class blue, but are mispredicted by the model. So it's kind of very specific also. For example, here, what we show is that, well, it's better if we have some, let's say, area or like space close to the given sample, that in this ball around the sample, we predict the same sample. So predict the same class, right? So we would like the model to be still complex enough to be able to learn such complex decision bundles. Now, how you can overfit? So basically, you can, for example, train too long in the given training sample, right? So the overfitting is, I would say, still I would say that not exactly the same as having more complex model, right? Because I can also, for example, have much bigger model, but for example, train for fewer epochs. So I don't overfit, but I can have more complex decision bundle. So for the robustness, we want the model to predict the correct class, even if we perturb the image using these size samples. Now, for overfitting, so then we have the standard graph. We have on the y-axis loss, on the x-axis number of, for example, iterations, and we have two losses, so train loss and the test loss, and we want the model to have roughly same test and train loss, so we don't overfit, right? So these are two different objectives. What we basically aim at, right?
Yeah, I mean, actually, for defense, we use more complex model. Yeah.
So for train, so what was shown in practice is that if you use more complex models, for example, like we had this comparison between resonance and VITs, vision transformers. Transformers occur to be more robust than resonance, right? Also, this complexity enables us to have this, more complex decision boundaries, but you don't have to overfit on these complex models.
Is there a specific aspect when you say it's more complex? There's going to be a lot of things. Is there a specific direction that helps to improve robustness? Or is it just increasing the number of parameters?
So I would say that okay. So in the case of the complexity, of course, it's only about the number of parameters, right? Here for the model. But regarding the robustness itself, you have many factors that contribute to the robustness, right? One of them is that, okay, we show that if you have a more complex model, you can express as more complex decision boundaries, and this model is more robust. But it's kind of one of the parameters in many other ways how you can make model more robust.
So if we are using, for example, regularization, we are decreasing robustness because we are decreasing model capacity.
Yes. Yes. So if you do regularization, then what is usually bad for is that you don't overfit, right?
Right.
Right. So here, for the robustness, it is well, it would mean that you don't overfit to adversarial examples, right? Might still help, right? Yeah. Mhm. So ultimately here, also this question, I think, on the forum, we still have to balance clean accuracy, so on samples that are not adversarial, and accuracy on adversarial examples, so robust accuracy. So doing regularization makes your model less overfitting, so it helps clean accuracy. And then you might have to check how it influences the robust accuracy, right?
I will linking robustness to accuracy only, that if it's highly accurate, so it's more robust in this case.
So actually, it is that usually there is a trade-off. So you might have a very high clean accuracy, and that model is not robust at all. And usually, if you want to have robust accuracy high and also clean accuracy, then actually usually you have to sacrifice a bit of clean accuracy. At least in practice, I have not seen that model has at the same time very high clean and robust accuracy. Okay. So next question is from Sina. Okay. Okay, so Sina has 4 questions. So in slide 19 for PGD, I confused with the idea of getting back from the first point out of the circle to the nearest point on the circle. Isn't the purpose of the attacker such that change the label and to get out of the circle? So, okay, so I think that's, let me just show you another slide for that. Okay. So, okay, you can start from this simple example. So, how does FGSM find adversarial examples, right? So FGSM is a fast gradient sign method, and then you only do one gradient step to find the adversarial example. Here, the epsilon is the epsilon ball around the given sample. So how much you perturb the image. So here, epsilon is in L2 norm. And actually, decision boundary is going somewhere through this actually epsilon ball. So, you know, in essence, you might go out of this epsilon ball, but still have the same class, right? So
Yeah.
you don't find, for example, the point is not to go beyond epsilon ball. Actually, the point is that you have to stay within the epsilon ball, because only then the example is not perturbed too much. So that, for example, for my eye, I could just look at the image and say, okay, probably this is actually image adversarial, which was basically perturbed so much that I can see has some artificial signs, right? So epsilon ball is to make sure that actually the image is perturbed in an imperceptible way, so that for your eye you cannot really distinguish between the clean and adversarial sample. And now for FGSM, what would happen is that I usually go to one of these corners actually to find the adversarial examples. So what I actually do is that I take the sign of the gradient. So this actually sign, in this case, would end up in the corner of this epsilon ball. Also, usually I clip the gradient to stay within the epsilon ball. Okay.
I believe that from all of the
Yeah. Yeah. Actually, so FGSM actually is L infinity norm. So actually, in this, so actually, in this actually case, you have actually the ball actually is a square. So okay, so this question is regarding this aspect. So if it's a L1 norm, then you have actually this kind of shape, circle for L2 norm, and the epsilon ball actually for FGSM is a square. It's actually L infinity norm. So you basically what is happening here is dimensions. Every coordinate is changed by maximum 1. So in this case, you can end up either in here it's -1, right? Or here it's basically +1, -1, all of this for corners. But actually, FGSM is based on the L infinity norm. This is why we draw this epsilon ball as a square. But
in the chain of dimensions, and there you turn the chain of
yes. So basically, just this epsilon ball is based on the equation. So basically, this is a definition of the norm. Yeah.
But there is no, for example, mathematical proof that it is unnoticeable for I to find out difference. It's just maybe intuitively it's the best one.
Yeah, I cannot give you mathematical proof for my eyes, unfortunately.
Yeah, that's right.
Now, so imagine that you have this decision boundary, right? So in this case, FGSM would fail because you basically constrain the attack to be within the epsilon ball, and then FGSM would go to one of these 4 corners, and then in each of these corners you stay within the same class. So you never find for example for FGSM in this case. But do you think that okay, is it possible still to find in this scenario, for example?
Can you use L1 norm here and still possible?
So FGSM works in a L infinity norm.
Maybe we can go in another iteration.
Okay. Okay. And then where would you go?
Again to the sign of gradient, and afterwards it makes sense that we can get back to years.
So I think that what Sina, right?
Yes.
What Sina is talking about is called basic iterative method, in short BIM or BIM. So actually BIM proposed this multiple small FGSM steps. So indeed, what we can do is that we can continue the steps as in FGSM, but also then actually we have to make sure that we stay within the epsilon ball. So we also clip the gradient to make sure that our perturbation is within the epsilon ball. And another aspect is that we also control how much really we move. So how big is the step with this parameter alpha. So we don't have to go full epsilon step or full possible length of the step. We just also can control how much in every single step the distance is incurred.
But if we are doing, for example, this one for 3 iterations, in that sense, we are maybe moving up to 3 epsilon balls.
Oh no, because you always clip, right? So basically here, so you start as in the previous example. So you have this initial starting point x, right? Then you compute the sign of the gradient and move with the small step alpha. So in a case of FGSM, you would move to one of the corners, but here you don't have to. You can just move with this alpha parameter, so smaller step, right? And then you would probably follow to to actually reach the decision boundary to be able to leave the given class. However, now you are beyond the epsilon ball, right? So then I clip the ball and I'm back in the previous class. So I didn't find adversarial example, but I can continue, right? I can continue this process, and then in the next iterations, at some point I can find adversarial example, right? Okay. However, what might happen is that this beam method, so basic iterative method, might get stuck in the local optima where it cannot escape from. So what's happening actually here is that optimization is trying, let's say, if it is attack which is targeted, so we want a different class, right? We want this class which is beyond this boundary, then basically optimization would tell us you should go this direction. But then we always end up in basically this case same class or basically outside of the epsilon ball. So we never can find the adversarial example. So what can we do?
Random stuff.
Very good. Very good. So exactly. So this actually can be avoided by adding this random start or even random restart, right? And this is actually what was also done in PGD. So projected gradient descent method. So we have this very, I would say, useful starting point. So we basically do this uniform noise addition, the starting point X, so the initial let's say, image or sample, right? And yeah, this actually helps a lot. So I did some experiments in the past, and adding this simple thing really is amazingly helping the search for the adversarial example. So how it works? Yeah, we just do random restarts. So if we're stuck in the local minimum, then we just do restart with this uniform noise addition. And then basically we can follow the different trajectory to find the example X, which is adversarial, which is from a different class, but still stays within the epsilon ball. So basically, usually how you do that is that you give to the algorithm a maximum number of steps. So for example, we have something like PGD 20. So we allow the PGD algorithm to make 20 steps. If after the 20 steps we are not successful, we just restart, and then we just do another 20 steps, but in different direction. So basically, you were stuck in this. So let's say we were stuck in this previous case. We allowed PGD to make 1, 2, 3, 4, 5, 6 steps. Maybe it's PGD 6. We were not successful. Then we basically go back to the initial starting point, and then actually we see that we can have this amazingly clear path to the adversarial example. But we just we have 1, 2, 3 steps, and we are there. So PGD 6. So after 6 iterations, you just restart.
By detecting when basically further search is going to be hopeless by kind of using like the loss of change, the loss of direction, or something like this. Well, I mean, I don't know if it's really a problem that we should just statically say, okay, let's give 20 tries if this really costs how much computation time and practice, or if it's not so much of a problem.
In practice, it's easier to just restart and just give to algorithms some maximum number of steps to perform. Yeah. Any more questions? Okay, perfect. So then question second. In slide 55, 56, I don't quite clearly understand how the magnitude and the number of the activation functions for the adversarial example is different from the left charts. Okay, So let's go back to this slide. Okay. So what's happening here in this graph? So we have here on the x-axis the channels. So this is actually channel index. So we have the last layer of ResNet 18 in this case. It has 512 channels. And actually we order the channels by magnitude of the activation. Actually it's not normalized from 0 to 1. Okay, but we just sort them out by the height of the activation. So now if we have ResNet 18, which is standard ResNet 18, this means standard, not adversarially trained, and actually what we see is that we have different behavior or activation magnitude for natural, this is shown in blue, or like pink, sorry, it's not pink, so it's a kind of, let's say blue, and then the yellow, which is for examples. So what is here important is that you have this much higher activations for examples, which also are in different channels, natural examples. And then if you do on-file training, so you train model to be robust, then actually what you observe is that you develop a more uniform performance, uniform activations for both natural and adversarial examples. So you want actually the model to really behave similarly for both the types of examples. But here you have clear distinction. The natural examples behave very differently than the adversarial examples. At least in the case of the activations and their magnitudes.
That's true.
Okay, and the same was here. So for the next slide, so actually here, so here the line goes like that. So basically it's increasing adversarial examples, and it's decreasing for natural examples. So also number of activations, and then once we train the model to be robust, naturally this also is more aligned for both natural and adversarial examples. Okay. Good. And then third question regarding slide 69. Are the high frequency features more informative for training of the machine learning models? Are they also generally more robust, or the low frequency ones are more robust? So this is slide 69, actually this one actually now. So here, what was the purpose of this slide was to show that models can pick up on features that are not really robust. What I mean by this is, let's say we have this classification of cats versus dogs, right? So in a non-robust setting, you basically have always, let's say, dogs in a grass, somewhere running, and then cats in house, right? Inside house, right? On a sofa or something. So basically, model might just pick up these features that are in the background, right? That's basically grass for dogs and sofa for cats, and always classify not based on what is in the image, which animal, but what's in the background. But these are non-robust features. Now, it was here shown that models really can pick up on some very specific high frequency features. So usually high frequency, why you talk about that here is because if you analyze the image in the Fourier domain, usually high frequency corresponds to some noise. So this is some high frequency noise. So it kind of doesn't matter for the classification, this high frequency noise. So this is kind of a method to show that, well, the models are not robust because they pick up on these high frequency features that are basically noise. So it should not be the case, right? Why is it happening? Because ultimately, the model's objective is to classify correctly. And the model, in this case, uses all the possible methods to classify better the given sample. So model basically overfits in this case, right? Or basically just, in this case, it even overfits to the data distribution, because there are these features that are non-robust in the background that the model picks up on. However, for a general classification task, it's important to have actually both high and low frequency features. So, for example, you want to classify if the image has snow or not. Actually, snow is usually low frequency. For example, like rain might be high frequency. It's kind of like everywhere in the image. And then, if you classify, okay, what is the condition outside? Is it raining, snowing, you have to take into account all the possible features, so high and low frequency features. So in this case, all of them actually might be useful for some specific task.
But generally, because you mentioned that high frequency can resemble noise,
Yeah.
Actually low frequency ones can be more robust, right?
So I would say if you have tasks like general, object in the given image, probably low frequency features are more important, right? But there are cases where also certain aspects, like maybe rain, is high frequency and should still be
That's
used for learning.
Yeah.
There's no like uniform division, learn only low frequency or high frequency. Like all of them can be useful for a specific task. For example, especially in the medical domain. So maybe, you have many chest X-rays and they look the same, but actually the disease is a high frequency specific aspect of the image, right? So in, for example, medical domain, high frequency is super important. If you remove high frequency coefficients from the like Fourier domain, in the Fourier transformation of the image, your classifier, for example, for a heart attack or something like other pathology might not work at all. Okay. And so Sina asked, I did not understand the concept of robust contrastive learning. Could you please explain this again? Okay, so we have raw CL. Actually, this slide. Okay, so I would say idea is very simple. So we want the model to give us the same representations for all possible versions of the given sample, right? We have initial sample X of this dog. We have some dog transformation. I think actually this is a vertical flip, I think. And also we have some other transformation here, maybe some random crop, and some adversarial example. And we want the model, this model F sub theta, which is actually a SSL model, to always give us the projection, the representations, Z sub I, Z sub J, Z sub K. So basically, it's very simple that it's the same as adversarial training. So we want the model to predict, in this case, same representations for all transformations of the given image.
And do we have negative samples here, like contrasting us?
We can have, yes. But the main point is that for the given sample, we want all the transformations, including adversarial examples, to give us the same representation.
And just one follow-up question that while I was reading the slides and watching the video, that some ideas that came to my mind that, for example, in adversarial examples, maybe can it be inspired by some architectures like GAN, so we can have discriminator and generator and optimize it to have better adversarial attack?
Yes, well, you connect GANs with adversarial examples.
Yes.
Well, the best attacks are those who focus on the given model, and actually the best are those who can really compute gradient. And this is by far the strongest attack.
Thank you.
So this method, just after the model is trained, we can then put different images or augmentation images to the model, get the output, and then make this projector to force them point to the same thing. That's the idea.
So actually here actually what I showed is that so what I'm talking about actually is optimization, how you can make these robust SSL models in a more efficient way. So what I showed here actually was that if you apply this raw OCUL or raw CL, then actually you would do training which is m sub n, m times n. So m is number of augmentations that you have to do for SSL. So like this T transformations, right? So you have m augmentations and n iterations to get these adversarial samples. So actually this raw CL becomes very, very costly. So n times n standard training, which is of course a lot of overhead. And then what was proposed is this DACL, so decoupled adversarial training, and they basically did a kind of two-step approach. So first you train this standard SSL model. So basically you have M times standard learning. You have M augmentations for the given image, and then you train student model based on the teacher model. So you freeze the teacher, which was trained with standard model for SSL, and then you train student model that actually should first imitate teacher, and second should also be robust to adversarial examples. So then actually here you also augment this example, probably with n steps, for example, for PGD, to make it adversarial example, and then you make also this model student FS at theta 2 to be robust, meaning that same representations for example and for the third example, and this is stage 2, which has only n times slower than standard training. So you kind of decouple these two stages. So first you do SSL training, and then you do adversarial training, and this decoupled approach gives you m plus n times slower performance compared to m times n longer training. Okay. Okay, so I think that we have 3 more minutes left. Okay, maybe one more question. Okay, I think that I don't know who is the person. So actually this is Anushka. Is Anushka here? Okay, apparently not. Okay, but I think that what we can do is that we can finish for today, so we don't have Anushka. So next time we start from the question from Ahmad, and we'll continue with these questions next week. And okay, we'll finish that next week, so that you also have all the questions answered before the midterm. Okay. Any final comments or questions? No. Okay, good. Thank you, and see you next week. Thank you. Huh?
I